System performance of series and complex RLC circuit. System analysis is conducted for the purpose of studying a system or its parts in order to identify its objectives. It is a problem-solving technique that improves the system and ensures that all the components of the system work efficiently to accomplish their purpose. In this presentation, we will discuss the two mathematical methods, namely the transfer function and state space model, and how they are used to determine a system's response and stability.
Transfer function model. Transfer function is a convenient way to represent a linear, time-invariant system in terms of its input-output relationship. It allows the separation of the input, the system, and the output into three distinct parts. It is a system analysis method that instead of differential equations, it algebraically combines mathematical representation of subsystems to yield a total system representation. From our previous laboratories, we have designed a simple and complex circuit. From our simple series RLC circuit, we have obtained this transfer function. From here, we can create the equivalent block diagram of the system showing its phase variables. Likewise, in our complex RLC circuit with two loops, we have obtained this transfer function and its equivalent block diagram below. From the two equations, we can assess that the only difference is the denominator of the transfer function in the simple circuit is on second degree, while in the complex circuit, it's on third degree. Now let us go to the advantages of transfer function. Transfer function is a mathematical model where we can obtain the gain of the system. Also, since it involves Laplace transform, the terms are simple algebraic equations with no differential terms present. Through transfer function, we can also determine the response of the system easily. In our case, we were able to obtain the response curve, as well as its characteristics through MATLAB simulation. From there, you can design and analyze the performance of the system to come up with your desired output. Lastly, the system's poles and zeros can be determined out of the transfer function. To get the poles, you just equate the denominator of the transfer function to 0 and get the value of s. Likewise, you can get the zeros by doing the same, but this time it applies to the numerator of the function.
Another mathematical approach to be discussed is the state space model. The state space model is a unified time domain mathematical approach that uses internal or state variables to describe the behavior of a system as a set of first-order differential equations. Generally, the state space model is formed by two equations, the state equations and output equations. The state equation gives the relationship between the system's current state and input to its future state, while output equation gives the relationship between the system's current state and input to output. In the equation, A, B, C and D are matrices. However, D is equals to 0 for most of the cases because it is the feed-through term. This model basically uses matrices and vectors to represent the system parameters and variables and evaluate the system via simple matrix algebra. Now that the basics of the modeling is discussed, we can now analyze the derived state space representations of the two RLC circuits. From our simple circuit, we have obtained this state space equation. Just by looking through the equation, we can easily identify what the inputs and output equations are. Since the first matrix is 2 by 2, we can assume that this is a second-order system and use two state variables. On the other hand, the figure shown is the state space equation derived from our complex RLC circuit. Now, from this equation, we can tell that this is a third-order system since the state matrix A is a 3 by 3. I also notice that the values inside the matrices are the same with the values in the transfer function equation but different signs. Aside from manual computations, we also use the MATLAB software to generate the conversion of transfer function to state space to verify if the manual computations are correct. As systems become more complex, representing them with differential equations or transfer functions becomes unwieldy. This is even more true if the system has multiple inputs and outputs. But the state space model alleviates this problem. One of its great advantage over transfer function is its flexibility and applicability to a wide range of systems, linear and nonlinear, time-varying and time-invariant, single input, single output, SISO, and multiple input, multiple output, MIMO. Unlike transfer functions who provide only input and output behavior, the state space model provides more information about the system internally using state variables.
System stability.
Here is our PZ map for the simple RLC circuit. As we can see, it has two poles and no zeros. This will be used later on to identify whether our system is stable or not. Using the Nyquist criterion, we have obtained this diagram. To determine a system's stability, we need to consider how many times -1 is encircled as well as how many poles or zeros are inside the Nyquist contour. And since the Nyquist plot does not have any pole on the right side plane and does not encircle the real value -1, we can deduce that the system is stable. Now, this is the PZ map for our complex RLC circuit. As you can see, the system contains 3 poles but with no zeros. Since this is considered a third-order system, it is possible to have 3 real poles, or 2 complex conjugate poles and a single real pole. The real part is the damping constant while the imaginary part corresponds to the damped oscillation frequency. On the other hand, we will notice that all 3 poles reside on the left half of the plane. This signifies that the system produces a stable response. To further determine and analyze the stability of the circuit, the Routh-Hurwitz criterion and its Routh array method was utilized. Its condition is that all the elements of the first column of the Routh array should have the same sign, either positive or negative. As we refer to the Routh array results, there is no change of signs on the first column. Henceforth, there is no poles on the right half side of the plane. Therefore, the system, then again, is proven stable.
Now, let us go to the system response and characteristics. We have here the response curve and characteristics obtained from our simple circuit using MATLAB simulation. Analyzing the curve, we can see that the amplitude is continuously decreasing with time. There is a huge occurrence of oscillation from the start, and it continues a bit as it approaches down to 0 or its equilibrium. This response curve from the simple circuit shows an underdamped response. An underdamped response is associated with parameters such as the rise time, peak time, percent overshoot, and settling time. Rise time, peak time, and settling time yield information about the speed of the transient response that can help a designer determine if the speed and the nature of the response do or do not degrade the performance of the system. From our complex circuit, we have obtained this output response. Looking closely on the simulated output waveform, the response curve also shows an underdamped response. We can see that there were oscillations before the system approaches the steady-state condition. If we will relate it from the PZ map and Routh-Hurwitz criterion, this system response curve of the complex circuit graphically proves that the results obtained were correct, and that the system is considered stable.
Learning outcomes. These are the things we have learned regarding the system performance of a series and complex RLC circuit. Transfer function is a system analysis approach that helps in the stability analysis of the system. It can calculate the output response for any type of reference input and helps in determining important information about a system such as poles, zeros, as well as the characteristics of equations. As systems become more complex, we discovered that state space representation is the best option because it can be applied to a broad variety of systems. Since it involves simple matrix algebra, which is highly compatible with simulation on digital computers, it is numerically efficient to solve and simulate.
Through transfer function and state space model, we can determine the system's stability. The values of the poles and the zeros of a system determine whether the system is stable or not, and how well the system performs. Also, we were able to understand how the zeros and location of poles in the S-plane affect the stability of a system. We also learned different stability and frequency domain techniques such as Nyquist and Routh-Hurwitz criteria that helped us further determine and analyze the constancy of the systems.
The response curve and its characteristics signifies the performance of the system. Through the use of MATLAB simulation, it can be proved that a step response can be simulated for a derived transfer function and state space equation model. This is important in analyzing and designing systems so that we can come up with the desirable output. Transient responses can be overdamped, critically damped, and underdamped. In our simple and complex circuit, both showed an underdamped response where most systems fall in this category. An underdamped system will be somewhat oscillatory, but the amplitude of the oscillations decreases with time and the system is stable.